Andy's going to be talking about, well, all that stuff there that's on the screen. Andy, are you still president of the CCHS? Is that your official title? Sorry?
There'll be no gym in about a month's time, so I might get kicked to the
curb. Okay. In any case, Andy's a key person in the CCHS, and he's been kind enough to help to work with us over the years to let the MicroPython meetup attend at the CCHS. It's been fantastic collaboration, I think. And I'm delighted to have you finally talk at one of these things. So, Andy, I'll hand it to you. And we do have about an 8 o'clock hardish limit. So let's see what you can do.
Okay, well, welcome. Thanks for having me on tonight. Hopefully it won't be a waste of your time. But tonight, just talking about distributed embedded services for MicroPython. So there'll be some of this will be large Python, and hopefully enough it will be small Python to little Python. So there's some the slides already online, and there's also 2 other previous presentations that I've spoken further about the system, but not about MicroPython. Okay, so I need to see what I wrote. So we're talking about talks in 2 parts. One part is about Aiko services, and this is the host side. It's all written in Python as a reference implementation, full distributed system that we use. That's open source. We use it at work. And the other half is about Aiko engine, which is the small thing that runs on MicroPython devices and works with the big system. Let's see. So this talk, I'll start with like a bit of a bigger picture thing. So some of the aspirations, but also some demonstrations, and also introduction to Aiko services, and introduction to MicroPython a bit, and a bit of a deep dive, but not too much. And other things is this is very much a work in progress. So it's been going for some time, but there's still quite a lot to do. So the big aspiration is to build systems across a number of different domains. So there's machine learning, which is that's my day job, and it's a pretty hot topic at the moment. There's media streaming to basically produce and consume media streams to I think big ML systems. Internet of Things, so in yellow, because that's what we hear tonight with MicroPython and Arduinos and things. And MPT is a messaging bus, and also robotics, which is systems like RGPart and ROS2 and stuff like that. And these are all quite different, but trying to build these ensembles of distributed components where it's everything is consistent and interoperable. It's not like a mixed bag. And so the problem with this is each of these frameworks has wildly different APIs and libraries and tooling and terminology. And so in the embedded devices, we often use MQT and some of the other buses as well. Modbus and Echelon, it just goes on and on. And a lot of stacks, there's like Thread and Matter might be material, might be becoming more popular these days. Then with streaming media, got GStream, that's a whole different kettle of fish. And machine learning has got there's just 2 big frameworks, TensorFlow and PyTorch, but there's so many other libraries and things. A lot of it's in Python, but not all of it. And with robotics, there's the ROS, which is another component system messaging bus, which is very widely used in the robotics arena, but you wouldn't see anyone in an enterprise system or an IT project using ROS for MicroPython. Just not a thing. And then there's all these cross-cutting concerns. So no matter what you're working on, you need to be able to configure and log, worry about security and failure and all those sort of things. And the embedded systems also got some really tight constraints like compute and memory. And so you're not going to be running your Kafka Kubernetes system on your MicroPython anytime soon. Although you never know. Yeah, so it's pretty challenging to write an application that encompasses all those domains. So I'm going to do a couple of demonstrations, and through it I'll be using this dashboard. So this dashboard this allows you to see all the services, and also the state of services, and it's all based on MQT, and you can use it to change things on the fly, kill things off, and look at the logging and all sorts of stuff like that. So. And that's one of the principles of the system. Everything should be transparent. No black boxes. You want to be able to see everything and interact with everything on the fly. Okay. So 4 demonstrations. Fingers crossed. Unfortunately, the robot didn't come up online because something's going on with the networking tonight. So I'm actually running off my hotspot at the moment. So half these demonstrations are not MicroPython. The other half do involve MicroPython. So let's see if I can have some success with this. So this one is demonstrating some machine learning stuff we do at work and some media streaming. So the idea here is this is all based on WebRTC. So up in the top left corner, there's some services on the network that represent devices, like there was an IKEA train set in the lounge room, which is running around the track. with a little camera detecting things, our office camera putting in the window, and also a neural network doing face recognition. So if I go to the train, now if I just go and have a look at the services, so at the moment there's about 6 services, and what's happened is when I select the train, what will happen is it'll create a new pipeline on the fly on this distributed system. So there's the train device there, and we can see messages over coming over MQT, like the its latitude and longitude, its speed and things like that. So this allows you to inspect. You can see there's currently 3 devices, and so on. Yeah, so let's start. So let's select the train. Hopefully this works. And so this is a pre-record. So this is the camera sitting on front of the train, running around the track, and as it sees trees and buildings and signs, it detects those. And in the back, you can now see a pipeline is being created on the fly. So this is using WebRTC, and you can see it's reading from video, and it's doing a filtering, and it's writing it back out. So that's just we'll just create a WebRTC pipeline on the fly. I'll just stop that. I can now select our office camera, which is in the city, just pointing out the window down the river, across the road from the casino and stuff. And that's live now. So that's an RTSP camera. We haven't looked that up to any machine learning, but the idea would be to be able to count trains and look for accidents and traffic and stuff like that. And you see once again, let's now start up a different pipeline where it's an RTSP pipeline reading data from the camera and then writing back out to WebRTC. And if I now go and if I just stop that, you'll see that now that pipeline has now been dynamically destroyed. And the last one is just hooking up some a small facial recognition. In this case, the inputs off the camera of my laptop, and up there, so it's doing face detection. That's me live, and you can see it's now created. It's running the deep face. Yeah, so that's some of the stuff we do at work. So it was one demonstration. The next one, if I go Alt 7, something like that. There you go. The next demonstration is and that's a bit of a conceptual view of what was going on. So you can see there's lots of services. There's white for the services and MQT messages. There's blue for WebRTC. There's a bus there. There's front ends, back ends, and as you build up these complicated systems, it's a lot to keep track of, especially if things go wrong. So that's kind of why we're building this. So the next demonstration I wanted to show is this robot. Unfortunately, it's not coming up on the network. But the idea is you can it's hooked up to a voice speech to text, and you can sort of talk to the robot and ask to do something and make it sit and wag its tail and raise and arm, pick stuff up. But I do have a video. Or maybe I could just skip that. You can probably just imagine it. But that's also done with these pipelines. We've got microphone from the robot goes to speech to text. That then goes through. It's not going through an LLM yet. That's the next step. Then it goes back and commands the robot to do stuff at the same time as we're streaming video and audio. So that's nothing. So
cool.
That's a Raspberry Pi inside that robot. So if I now go back to slideshow, maybe. So the third thing I was hoping to show is this little jukebox. So it's so let me see if I can go to the screen now. So let's go here, go here. Right, it should be fine. I'll just bring the dashboard up. So this is now pointing this instead of pointing to a system up in AWS where we're running our work stuff. This is just pointing to a my server at home. So actually on that server at home, you can see there's already 5 ESP32s running MicroPython just sitting on there as little services, just for fun. This time, and so start this jukebox up, and that brings up a Python user interface. But also you can see in the back end on the registrar, you can see it's put up a pipeline for the jukebox, which has got that's going to be audio in for once we've downloaded a song, and it's going to put that through a fast Fourier transform and send MMC messages to our MicroPython device, which is just here. That cable's only for power. Let's see if we can. And that's so it's also flashing green there, which is pretty good because it means it's on the network. So someone says think of a song. Actually, oh yeah, that's good to go. Song, anyone?
No one
listens
take it
to
off. Taylor Swift.
Staying Alive. Oh my good. Staying Alive. Hang on. I cannot hold things and type and think all at the same time. So this just goes and does a YouTube search. That's found Staying Alive. and we play it, it's actually going to have to download this because I don't listen to the Bee Gees that much. as iconic as they were, it's not a disco dance, I'm afraid. So once that comes down, yeah, it's maybe it's already come down. So let's see if we can play it.
Yeah.
Maybe
We're alive.
I don't think it's downloaded yet. This is the problem about the networking being dodgy. Yeah. Oh,
I just realized.
I was too brave to basically ask for something that I didn't already have cached. I'll just try again. So Bit Licky. Oh, I don't think that was the name of the song. That sounds like something my dog would listen to. Okay, so that's Daft Punk. And if I play it, oh, demo file. That's really unfortunate. Oh no, here it is. Oh, there's no the audio must be going somewhere weird. Oh, I know why. Here we go. I turned the audio off not to mess up the presentation. But basically, the FTT is having a laptop, MQT messages coming down to the ESP32, and so the idea here is yeah, it did work after all, just didn't have the volume on. But the main idea is it's really a combination of backend and MicroPython to achieve something you couldn't do on MicroPython alone. So okay, so now hopefully this is starting to make sense. And then so that's another quick one. And what was happening there is that little Python user interface actually kicked off one of these distributed pipelines. So you can wrap these things in user interfaces if you want, if you're so inclined. And last one to sort of kind of demonstrate is this badge. So I'll just take the LEDs off. So this is just one of the conference badges we did for LCA, and so it's just got an ESP32. I don't know how close I have to get to the camera. Is that close enough? So you can see there's two OLEDs that are showing some status, and they've actually got little buttons behind them. There's touch sliders. And you do things like if you touch both those at the same time, if the system user face might come up, maybe. Oh, there we go. Yep. So it's basically like running. Well, I wouldn't call it an operating system. It's like a little bit of a framework there to allow you to handle buttons and messages and displays and that sort of stuff. That's what the MicroPython engine does for you. It gives you not only can this thing appear as a service, as a distributed service, but also gives you a framework for handling some common things like like NeoPixels and screens and buttons and stuff. So that's kind of hopefully gives you some sense of what this talk is about. I hope. Let's get back into it. Okay, so that's some So that jukebox just shows you there's a user interface and YouTube search and FFT running on the laptop, and then MicroPython's just doing the visualization. Another thing I've got is isn't finished yet. This is going to be a cloud for the space. So there's 150 LEDs on here, and that little 8x8 screen will be replaced by this cloud of 150 LEDs. And so it's hanging in the space, and when we have our Saturday night sessions, so this is a big music visualizer. Or maybe,
Oh, that's so cool.
That's and so got a few other bits and pieces there, but that's complete. Okay. That's the badge. All right, so there's a lot of history behind all these projects, but one in particular is for the Open Harmony Conf for the Linux Conference Australia. So for about the last 13 or 14 years, we've done about 12 or 13 projects. And this is sort of color coded. There's white for Arduino projects. There's about 2 or 3 Raspberry Pi ones. There's even an ESP8266 before the ESP32 came along, and so at least 6 or 7 projects have been ESP based and MicroPython. So one of the problems is when we're doing hardware projects, you get hardware gets done just in time, and you get like one evening to write software or firmware. And so the idea of actually building up a framework over time that allows you to build up, make the hardware functional as fast as possible seemed like a good idea. So that's one of the places this came from, is making the software development faster. So now just talk about these things in more detail. So Aiko Services is the distributed system framework that allows you to run things from small machines right across into the data center, build these pipelines that run across the whole internet and deal with failure. And there's the GitHub repository for that. And the Aiko engine is a specific implementation of this for an embedded controller for MicroPython. And I've done ones in C. We've got things in Go and JavaScript as well. So it's now different cross language. Okay, so what is one of these services? So service is basically anything that can join a distributed network and then ultimately then be discovered by other services, preferably dynamically on the fly, because you want to be able to have networks to deal with failure and also self-healing. And the other thing you can do is can receive messages, and if you move MQT, it's usually done by topics, although typically people hand select what those topics are. In this case, the system automatically creates a topic for you, which I'll get to later. And you can and the service has fields. So you've got the topic itself, the name of the service, who owns the service. So say I created it, someone else did. The transport that's using. So this uses not just MQT but some other transports like ROS. So if you're using ROS, that just appears just as more services. It's just seamless and transparent. Such a transport independent. And you've got these tags, and tags are just like how you use tags for sorting your email on Gmail, where you can basically tag things and find email by filters that way. That's how you find services. You might say location equals kitchen, or device type equals light. And so you don't use MQT topics to find stuff, or not, you use the tags and other methods to find what you're interested in. Because the problem with MQT topics is you go, okay, I might make the topic location and device type, so kitchen lights or kitchen temperature sensor and lounge and so on. But you go, oh no, really the other way around. I want to find all my lights, and just so it's like a file system tree. It's like you're stuck. So the idea of the system dynamically choosing the topic for you, and there is a structure to it, but then using these other techniques to find your services is one of the key things we're doing here. So one of the main services is the registrar. It's the service that allows you to find other services. And so when something like the SP32 starts up or anything else, basically they can send a message. They can discover where the registrar is. There's a static topic for finding the registrar. And after that, use the registrar to find everything else. And so just add yourself to that using a small S expression for those who are familiar with Lisp, the one true language. And you can sort of add yourself, remove yourself. You can share your state, and you can also get history of services. So nothing worse than you start something up, a microsecond later, sort of millisecond later, it dies, and you go, oh, what just happened? And the system what we do is that we record the history, so you can see things that were there temporarily and unfortunately died. And so you've got things like the services cache that so you have to write all this code yourself. There's the instantiate services cache, and then you now have a cache that has all the services that can be discovered by a filter. And there's also active discovery, so you can discover other services as well. So from a high level perspective, there's a service called the registrar, and then if you have you create service 1 and service 2, they also add themselves to the registrar. It's all done with MQT messages, and then they can find each other, and then they can just publish messages to each other. So unlike I'd say most people's use of MQT, where most confine yourself to just sending application messages, like temperature values 32 Celsius, like that. I think it's rare to find people actually using MQT for the entire system. So the actual system itself interacts and finds it and operates by using MQT. Ooh. If you're anyone who's familiar with the actor model, that's a very powerful but very simple way of designing your distributed services, where basically you have each actor has its own inbox. An actor can send messages to other actors. These are dealt with one at a time by the other actor. An actor can create other actors, and those sort of three operations allow you to create pretty much anything you want. But it's sort of more constrained and easier to reason with than just having a free for all, like fully multi-threaded services and do mad things. So some principles are the whole system is designed as an API. So effectively, I think of everything as function calls. Those function calls get turned into Lisp expressions, so which then gets across the network as MQT messages. So it's really I guess programming or program oriented. If you think it's like just sending function calls, except they're just a little bit slower because they're going across the network. Everything's Lisp because it's basically more powerful and it's more succinct and more powerful than JSON, because it's also a programming language, so you can actually send mobile code across the network. So you can send computation to other places. Security needs to be kept in mind as well. And it's also nice to have human readable messages. It's so much easier to diagnose stuff if it's simple and you can read it. It's not sort of encoded in some fashion. Obviously, if you need to send high bandwidth, low latency data like video and audio, we use an appropriate codec for that. We do that out of band. So the software is really for the control plane of your system. Yeah, I'll skip the rest. That's fully asynchronous, low latency. So none of this sort of making a call, waiting, and which may or may not get back to you, and then you have locking. So you send something off, and you can use eventual consistency and other asynchronous techniques to get back to the state. So it's actually in a way faster. So ahead of time you say, I'm interested in such your state, like maybe it's your logging level, are you ready, or what any temperature value. So you're just interested ahead of time, and then after that device is telling you at an appropriate refresh rate what the state is, you just look in your cache. So it's actually faster than saying I need a temperature, doing a blocking call, and doing a get and waiting for it. Okay, so that's the broad system. Now let's talk about the MicroPython stuff, which I assume is by most people here. So it's basically at its heart, it's a simple implementation of the services protocol. It's not everything because they're only small machines and they only need to participate in a simple way, but they are first class citizens of the network. The MicroPython devices. It's modular. You only have to import what you need. I do need to clean it up a bit. It needs to be tighter than it is, but the idea is you only import. If you want buttons, great, you want those. If you want network, get that. You don't bring the whole thing in because there's no room. And it basically provides an event loop. So it's inversion of control. You define everything as handlers. You add those handlers to the system, and then off it goes, like you're writing the user interface. So it supports empty messages, timers, buttons, all those sort of things that generate events. They just basically get routed to the handlers that you write. It also supports screens and NeoPixels, the sort of stuff that we've been doing during conferences. For things for like Wi-Fi, simple stuff like it remembers the SSID password for multiple Wi-Fi places. So when you can be at home, work, hackerspace, and the device hooks up instead of just having one. It's a simple idea, but it's helpful. And if the device can't get onto the network, it comes up as an access point, small web server, and so you can use your phone as a user interface to configure a new Wi-Fi access point to your device. It just restarts and it's good. So because most of it, often these P2 don't have a keyboard and screen on them, so it's just these little things that are simple but really helpful. It's all kind of built in. Yeah, so it's got a web client, web server. You can do over-the-air firmware updates, so there's probably better ways of doing it than how I've done it, but it's still there. And also it can act as a hardware test harness, so we can plug two of these boards together and have one test the other. So say I want your outputs this way because it's all done with messaging. So it's all these sort of handy things. So if you're writing code, as we all know, MicroPython boots up domain.py. Some of the machines I know, and you can see it's mostly just importing the things it needs. One thing I've found is that when using MicroPython or something on the host side, I know if you can use the web browser and other things, but if you're doing it across the serial line, is that as soon as you start writing to the output, the serial line is doing like triple duty, I think it is. It's like it's acting as a console. It's a way of transferring files, plus it might be your application output, and things can get a little bit confused. So what I've done is you can when it boots up, it looks at these. If you're holding this, touching these two pins, the framework just immediately drops out. So things like whatever you're using, some sort of command line file transfer or thorny or whatever it is. So I've found that extremely helpful, especially with newcomers. It'd be quite confusing. Why can't I talk to my MicroPython device? Does anyone else find this a problem? Maybe. Yeah.
When stuff starts going to sleep.
Yeah, it's nice about it. Yeah. So but it brings out that stuff that and then what it does is a parameter called application. So I'll talk about configuration in a sec. And so you can have multiple applications in your main so it's configured, and the main program will start that up. It calls your application initialize method, which I'll see in a sec, and then just goes into the event loop. That's main.py. So in the configuration top level directory, there's a whole lot of little Python files. Everything's just really configured as small Python dictionary. It's just there'll be parameters. So for the led.py, there'll be like how many LEDs on your NeoPixel strip? What is it linear, or is it two-dimensional like a panel? All that sort of stuff that's in led.py. Main.py has things like your application sign. MQC has some MQC configuration sign that has your Wi-Fi passwords and so on. Yeah, so it all just there is a simple little Python files. And system UI, that's that thing if you hold the buttons down where the UI comes up and shows you console and firmware updates. That's all there. So that's the configuration. Your application skeleton, I've just mentioned the initialize method, so it's down the bottom in orange. So the main code will just call your initialize. That's where you can set your handlers up, timers, message handlers, and so on. And so I've got two examples here. One is there's a handle timer and handle pins, just to make sure that you're checking the pins. Maybe 20 hertz, which is pretty decent. And then the handler gets called, and so you can have multiple timer handlers, software timers. So things going like once a second, once a minute, once every hour, and this list has a stack of timer lists. And then you can have all your message handlers. So if an MQC message comes in, that queues it, so the MQC handler can return, puts on a little queue and handles that way. So that's how most things work. Here's how we so for buttons to support basically straight buttons. So on this device, we've actually got buttons behind the other screens. This is a bit of an experiment. So is that touch buttons? So these are touch buttons here, or even sliders. So you've got little classes for each of those combinations, and you can do things like have what if you press multiple buttons, and then your handlers just get called under those circumstances. You're going to press and release events. So that's all there for buttons. Now, it's not too hard to write code for one button, but over here I've got a device. It's got four joysticks. That's 16 buttons just there, plus plus 4 other buttons. So that's got 20 buttons on it. So it's nice just to have that all sort of kind of done Past me looked up future me. Past me is good. Future me sucks a bit. Yep. So there's buttons. There's also some code for neopixels. So it's just simple things like fills and lines. Handy for panels. Things like you can set dim. So basically, sometimes these things are super bright or consume a lot of power. So you can say set dim across the board. Just helpful things like that. And I can show that off in a sec. But the other thing is though that all those functions also get wrapped as MQT messages. So that's how the spectrum analyzer was working before with the jukebox. It was sending sending MQT messages to the device. Effectively, it's list function calls. Clear, draw a line, do that sort of stuff. And so that's where this idea of having function calls everywhere is kind of one of the heart of the system. So and similarly for OLED, we've got just do some other handlers, which often just map straight through to the OLED library, but also can do things like these two OLED screens here are actually kind of like one big screen. So if you send a log message, it'll go across to both of them, and things like that. So also it's got things like titles, and also the state of the networking and MQT up at the top here. It's like little enunciators, so you can see these little characters saying, "Oh, I'm on Wi-Fi. I'm on MQT." So this is and also how much memory is left. So and if you do a log message, it sort of scrolls up. So just all these kind of handy little things that are built in. And similarly to the LED, there's a set of MQT messages that just map through the same functions. So you just move all through MQT. So it's sort of like having like a tiny little graphics language for these sort of things in minds. Okay, I'll see if I can demonstrate that. How can I do that? Thanks. Here we go. I prepared this earlier. So I'm just going to send mosquito pub messages. So hang on, I'll need to connect it back up again. I do not like connecting things up when they've got power on them. This always goes terribly wrong. In this case, I got away with it. Okay, so it's going to be really simple just to show the concept. But I'm just sending a message to gosh, it's not easy to do. Right, so right. This will send a pixel to green, and then I do a right. Hopefully that worked. Oh, there we go. So you can see it's a green pixel. Then I can send a clear message. There you go. Yeah, so it's just sending so those you send function calls across the network, which send it to function calls in MicroPython. Okay, so there we go. Time for questions. So in the GitHub, there's a bunch of other applications and examples. I've really got to work on the documentation across the board. It's been curious of coding. Maybe ChatGPT. I'll just throw the code at ChatGPT. Say, document this for me, and do my work, and I'll go to the beach. Yeah. So at least there's some examples to show how this all works. And they're the resources. So the GitHub repository, and the two other presentations. So from here, apart from just improving the documentation, examples, the testing and so on, I'll be hopefully in a few months be doing the ML presentation. So far I've done the overall presentation at the start of the year. I've done media streaming at PyCon. I've now done IoT tonight, so it wasn't too terrible. And in a couple months I'll be doing the ML version, and then sometime after that I'll be doing the robotics ROS2 version. So across through that time for that. So hopefully get that done, and then just keep building it out further. Yeah, so we're going for time. So any questions, perhaps?
Context, are there any restrictions in regard to the types of communications channels, essentially? So could it be using NB-IoT, LoRaWAN, Sigfox?
Okay, cool.
That's
all right.
Type of area.
So the first, okay, so the question was when it comes to communications, and it's not so for IoT particularly, but could be for anything really outside of that domain. Is there any limitations, like is it only restricted to Wi-Fi and so on? And the short answer is, well, yes, there's a limitation that there's only so much code written, so I don't do all these things out of the box. So I'm not going to cheat and say, oh, I could do anything. That seems a bit of a cheat answer. So at the moment, I'm primarily supporting TCP/IP as a lower layer,
yep. And
then affecting the sockets. And then above that, I'm supporting about 3 different transports. So MQTT, Ray, and ROS2. So that's where it's at the moment. But what I've had taken care of is everything's layered. And everything's pluggable. So if you don't like a particular transport, you can swap your own in just through configuration. So I've thought very heavily about expandability, and that what's popular today may not be popular tomorrow. So you just plug something in. So things are pluggable. So future expansion is very well catered for.
a typical dialogue packet size.
Mhm.
That's what we're talking about. We're talking bytes, we're talking kilobytes.
Well, it's very application dependent, but often what two things happen really is that you try and put your compute where it needs to be. So you don't want to be sending these really complex messages across the network. You basically say, I'll do my computer on the device and send something like clear the screen or just like that. You know, I could have sent it like 2,000 pixels worth of zeros, or just say no, just clear. So and also so you can basically through good design minimize the packet size and the number of packets because there's ultimate limits, especially on small devices. That's my recommendation. But there is the system itself, like MQTT itself, can have a packet size up to I think 2 gigabytes, which I don't know. I've never ever seen someone send that, but it's in the protocol allows that. I mean, that's insane. But certainly I wouldn't recommend it. I've sent like slow speed video over using this. Something because machines are on secure AWS services, and we've got all the privileges up. It's actually sometimes easy for me just to send a frame of video across MQTT and go, oh my god, I could set up WebRTC or something like that to get through. So you can be correct. So there's no immediate limitations apart from network bandwidth and latency. But sensible design is a good idea. Oh, sure.
Regarding the MQTT protocol, is there a concept of ownership in that? Let's say a device would be registered to a particular person, and then there would be a secure topic only for that person to subscribe to. Because
Great question. Really long answer. So the question is about in MQTT, is there any concepts of ownership? And so the MQTT protocol itself gives you username and password. So when you connect, you can have username and password. So the server knows that. You've also got TLS to keep it secure. And then I think after that, it kind of depends upon the server. So I use Mosquito a lot. And what's wonderful about Mosquito version 2 is they came up with the dynamic security, where what you can do is you actually send MQTT messages. If you've got the privileges, you can send MQTT messages to create roles and access control lists to topics on the fly. And we use this heavily at work. And so one of the things, what we've done in Aiko services is the topic path that's chosen is a namespace / the host name your service is on / process ID / service ID. So that gives you pretty much a unique topic path for all your services. And also it's kind of meaningful. You can go, we can have like a production or a test namespace, and you can use security to make sure your production is using the same Mosquito server, and your production stuff can never get touched by your test stuff and vice versa, or an Andy namespace. So the namespace is picked that way. And then you can see the host and process ID. So I'll call that process off, and that gets rid of service. So that's kind of that's how that's sort of chosen. It also ties into security, because now what I can do is basically say that username with that password can only access the namespace prod, and that's it. And that keeps everyone else out of the prod stuff. So yeah, so MQTT provides some great mechanisms, and I heavily leverage off them. I also love Last Will and Testament, and there's a few other things as well.
so when the device actually is onboarded, it has to be registered to a particular user.
Okay, that's another world-class problem. There's things that you don't try and solve yourself, and so pre-shared keys back now, since property has been a thing, key sharing has always been a problem, and so that's where public-private encryption is helpful. Problem there is though these are quite small devices, so you really need to have SSL support kind of on your device, and also needs a bit more memory. So that's why ESP8266 were never really going to fly commercially, because they didn't quite have enough memory and stuff to do that public-private key. So yeah, so when it comes to handing keys around, what you need to do is when you ship a device, you bake in your the public key of your organization or your team, whatever, and then only your team can sign software or any configuration, anything that's important. Only your team can sign software that the device would accept using its public key. So yeah, so you need to ship your public key with all your devices, and then you pretty much do whatever you want. So a few people nodding, so I think I must have got it not too far wrong. There we go. So that's just after 8. So hopefully that was interesting. But certainly something I love doing, and happy to chat to anyone about it. Awesome. Thank you very much, Andy. No problems.
Thanks, Andy. That was awesome.